Now, let us see some fire sources and try to classify them based upon the um hazardness of this. So, would for example, say domestic fires, for example, domestic fires. In domestic fires, wood, because in the many domestic thing, wood appliances are used, even for construction, wood is used, etc. Similarly, polymers. So, see, a liquid monomer can be polymerized to take a polymer like say PMA plastics basically. Then cooking oil, fabrics, cloths, etc. Can be sources for domestic fires. Okay, in a home, domestic fires, these are the commodities which can cause fires. Now, take industries, solvents. So, ethanol is a solvent, acetone is a solvent. These are all fuel, flammable solvents. Then, several gases are used in several industries. Okay, LPG, the natural gas, etc. Now, there are several other flammable chemicals which are used in industries. These become the source for fires in that. Then forest fire, the vegetation, natural vegetation, forest itself is the source for the forest fire, very huge scale. So now let us come to classification. In the classification part, fire is classified because basically there are several types of classification possible, but this is basically done in USA. Classification is A, B, C, D, and K. These are the 5 types of fire sources what we can have. First one is class A, involves wood, paper, other materials, cellulose basically you can say cellulose materials. Generally, this wood, paper, etc., when you burn them, it produces a carbonaceous particle and a ash, char. So, that is the class A fire. Class A source of a fire involves charring solid fuels. Okay, now as I told in the beginning, when the charring solid fuel is heated, moisture and volatiles are released and then a char is formed. This char, which is carbon plus ash residue, will have a reaction involved at its surface due to its temperature plus oxygen coming from the ambient. The volatiles which are going out of this will have some fuel gases. This will react with the oxygen from the atmosphere, constitute to gas phase flame. And the heat feedback from this particular gas phase flame is important for continuous feeding of fuel to the flame. Now, when the volatiles are released, a char surface, carbon and ash surface is formed, and now when it is hot enough, say 900 Kelvin temperature, then oxygen from the ambient diffuses and surface reaction takes place, smoldering. Now, how to quench these fires? First of all, you have to use some agent. So, quenching agent, normally water is used because when you sprinkle water, the fuel surface will become first cold. The fuel surface becomes cold, that will lead to basically it will cut down the fuel supply. Even if moldering occurs on the surface, when you sprinkle water, the smoldering reaction will be inhibited. So that is the main thing is water based system can be used for class A fires. Class B fire involves fuels like liquid and gas fuels. Okay, so flammable chemicals, solvents, alcohols, ethanol is also a solvent used in several industries. So this contributes to class B. Some gases also CNG, LPG. So these fires are class B fires. Okay, now when liquid fuels are used, vapors are formed over the surface. Please understand that evaporation process is a surface phenomena. When surface is heated to a particular temperature, vapors come out and there will be vapor pressure. imparted to the surface. So this is surface phenomena. So if the boiling point of liquid is say 120 degrees, when the surface is even at 70-80 degrees itself, you will see that uh, required quantity of vapor can come out of the surface and contribute to the flame in the gas phase. So it need not boil, the liquid need not boil. Surface evaporation will contribute to the fuel vapors from go to the flame zone. Now, as I told you, the heat feedback is extremely important because the flame supplies the heat to the fuel surface and sustains the evaporation. Okay, so when the surface is heated, vapor leaves. So there is a mass transfer from the surface. Heat transfer from the gas phase to the surface, mass transfer to the surface to the gas phase. So heat and mass transfer are coupled. If there is no, see for example, if there is a delayed heat transfer, then mass transfer cannot occur. So that means that the fuel vapor cannot reach the flame surface. So the coupling between the heat and mass transfer is important. Rate of burning of liquid fuel depends on what is called a property called volatility. Volatility is nothing but how fast the fuel will vaporize. Okay, if you take say diesel, take petrol, I will say petrol is volatile because it is easily evaporatable. I can easily evaporate it, but diesel is not easy to evaporate diesel. Okay, so that is the difference between the same, say for example crude oil gives this, after distillation of crude oil we get petrol, diesel, etc. But based upon certain properties of these fuels, okay, the fuel volatility will change. Some fuels can be easily vaporized. For example, petrol. Some like diesel cannot be easily vaporized. Low volatility fuels. Now that is one of the important thing. The rate at which the liquid fuel burn, the one of the important thing is what is the rate at which it will evaporate, because that is the first important step for a liquid fuel to burn. Further, you need good ambient conditions. That is, if the heat feedback is good, then heat feedback comes from the ambient surroundings or the flame. Surface is solid, the liquid surface, surrounding is the gas phase. So the ambient condition also will dictate the heat feedback from the flame to the surface, which will again sustain the evaporation. Then gas phase convection. Okay, now let us take a liquid fuel in a beaker. Now some vaporization occurs and the fuel vapors are formed. Fuel vapors accumulate over the surface. It is formed over the surface. So we have a definite surface vapor pressure. That is the pressure imparted by the vapor on the liquid surface. So now, if the gas phase convection is strong enough, then the vapors will be removed. Then more vapors can come in. That means the evaporation rate, further to that, the burning rate will increase when there is a gas phase convection. So the rate of burning of liquid fuel depends on a property called volatility, which is not a single property, it is a multiple property. We will come to that. That is basically the rate at which the fuel can vaporize. Then only the vapors can be supplied to the combustion zone. Then the ambient conditions. If there is too much of heat loss, then the heat feedback to the flame can be reduced. So ambient condition will dictate the rate of burning. Then the convection in the gas phase. The fuel vapors which are formed over the surface should be removed as soon as possible, so that more vaporization will take place. So these are the three things which we have. Now the gaseous fuel, let's say gaseous fuel, there is no primary step which is required. For example, already gas fuel comes out, then the only important step is how it mixes with the oxygen, or how it is carried to the flame zone where oxygen from the other side comes and meets it. So So that means the additional rate limiting process like evaporation or gasification, evaporation of a liquid fuel or gasification of a solid fuel is not required. That means these gas fuel flames can be much faster and hazardous. So it may give, so the rapid burning of gases can take place, so it may be hazardous in nature. So class B fires involve liquid and gaseous fire, fuel fires. Now, how will you quench it? Is using foams for the liquid fuel fires. Okay, see, when you cover the fuel surface with something so that the evaporation stop, then in the fuel, the fire triangle, the fuel is cut off. That means the fire will put down, fire will be quenched. Okay, so when I inject what is called a foam is a very complex molecule. The foam when you inject, this spreads over the liquid fuel surface, thus allows no mass transfer from the surface to the gas phase. So what happens is fuel is cut off. So aluminum industries or copper industries, copper industries use lot of kerosene pools as solvents. Now, when this pool catches fire, they apply the foam over the fire so that the surface is covered with the foam and the fire is quenched. Okay, now chemical reaction for gaseous fuels, what to do? So, you can also use water to some extent, but if you have some agents are some suppressants which will inhibit the chemical reaction itself, then that will be the best for quenching the fires from gas fuels. Okay, so that means, if for example, if I have some halon injected, then the halon can directly participate with the reaction mechanism and quench the fire. So we'll see about this later in the last chapter. So the main thing is, when you want to quench a fire, the fire triangle should be inhibited. For example, if you spray water, temperature is reduced. Then water comes to the surface for the solid fuel, and so solid fuel there is no issue. But if liquid fuel, if you take, say for example, there is a diesel pool which is on fire. If you supply water to this, nothing will happen. The water will go to the surface and it will go to the liquid fuel pool surface, and it go, because of its higher density, it goes below that, and the diesel will be on the top, and the contribution to the fire will still be there from the, as a, see, contribution of the liquid pool surface producing diesel vapors will still continue. So for liquid fuels we cannot use water, we have to use foams. For gaseous fuels we can use water sprays or halons type of agents which actually will inhibit the chemical reaction itself. Then come to the class C fire. Class C fire occurs from energized electrical device. Okay, energized electrical devices, electronic devices, computers, motors, transformers, etc. are the examples. So electrical fires, they occur due to, say, electrical short circuit or something like that. So that means there is a chance of getting electrical shock, etc. Then a spark can be produced which can reignite the fire. When the fuel and oxygen are present in some proportion, when the spark is produced, it may reignite this. So fire hazards commonly include the products, toxic products, smoke layers, etc. Apart from that, electrical shock and reignition can also occur due to a class C fire, which is due to the electrical fire, basically due to the energized electrical devices. Now, how will you quench this? You cannot use water. So, you have to use, for the class C, dry sand. Okay, dry sand or some powders. Okay, some powders can be used to quench this. Basically, when you do that, first of all, you have to switch off the power and try to use the dry sand or these powders to quench the fire. So why you use this? Because when you use some other substance, it may be reactive with the metals. But if you do use this dry sand or powders, then it will be non-reactive. And also these are non-conductive, which is what is required to quench the fire. So this is about class C, energized electrical devices. Class D is a specialized category where combustible metals, see even some powders of metals like iron, aluminum, etc., can be oxidized. Dust, the metal dust, we can say, very, very fine particles. The fine particles has more surface to volume ratio. When they are hot enough and oxygen is also available, then the fire will be formed and the temperature will be very high in these metal fires, 2273 Kelvin. That may be the temperature basically. Okay, now class D fires, combustion metals also are quenched using dry sand and powders, because if you spray water, water can react with the hot metals and produce H2. This is a dangerous thing. So water cannot be used. Okay. You can also use halon, etc. That's no problem. But the other alternative for quenching the fire will be dry sand. So sand is a very good thing. So sand you can use. Probably the cleanup process will be somewhat tedious, but quenching the fire and saving the structure, etc., will be possible when you use dry sand or powders in the class D fire, like in class C. The final classification of fire is called class K fire. The class K fire occurs from sources like cooking oil, greases, animal and vegetable fats. Okay, cooking oil. So you can observe this burning of cooking oil in your house itself. When you try to fry something in a vessel pot where you have a oil, if the oil temperature increases beyond a particular value called fire point, and these oil vapors are coming out from the surface, which can mix with the atmosphere oxygen, and at particular condition you will see that there will be a ignition of this oil surface and the pot carrying the oil will burn. Basically the oil in the pot will burn, having a surface over its flame over its surface. Okay, so the class K fires are constituted from cooking oil, greases, animal and vegetable fats, because organic materials, you can say some organic materials, some greases, inorganic material also can be included here. To quench these fires, as I told you, these materials like cooking oil, greases, animal and vegetable fats have a certain temperature called fire point. If this material is heated more than this temperature, then a fire can happen over the surface. What is used to quench the class K fires are wet chemical agents like potassium acetate or potassium carbonate. Potassium acetate or potassium carbonate is used to quench class K fires. So these are the classification. Class A is basically a charring type of wood, cellulose material, and you can also have papers. Class B is liquid and gaseous fuel. Class C is energized electrical devices. Class D is combustible metals. Then class K is basically cooking oil, greases, animal and vegetable fats. So these are the classification, and for each class of this, the hazard level is also higher. So for example, combustible metals and the energized electrical devices are very hazardous, because there are a lot of other phenomena which is going to occur simultaneously. Class K fires basically gives us some, for example, these are all some materials which carefully we should handle, so that we will have no, these are domestic fires basically which can be avoided. Cooking oil, greases, animal and vegetable fats. Okay, wet chemicals, potassium acetate or potassium carbonate will be used to extinguish these fires. These are the classification basically. So, properties of combustion materials we will see next. So, basic important property of a fire source or a combustible material is its calorific value. Calorific value is the heat released when 1 kg of material is completely burned. 1 kg of the material, fuel material is completely burned. So, that is the main property. Then you have other properties, important properties, which in as a group called thermophysical properties. They are thermal conductivity K in watts per meter Kelvin, specific heat C in joule per kilogram Kelvin, and density kilogram per meter cube. Okay. So, now these are all very important thermophysical properties of the fuel. From the thermal conductivity, specific heat and density, these three properties, you get two more properties. First one is called thermal diffusivity. Thermal diffusivity K by rho C. K by rho C is called thermal diffusivity alpha. So, now alpha is an important thermal property. Then in fire scenario, okay, another property which is product of rho, K and C called thermal inertia is also an important property. Thermal inertia is product of density, thermal conductivity and specific heat. K by rho C is alpha equal to K by rho C is alpha, which actually has a unit of meter square per second, thermal diffusivity. Okay. So, these are the important properties which are there in this. Now, for a given fuel to burn, what is the required quantity of air? That is estimated theoretically, and that amount of air is called stoichiometric air. Stoichiometric air is nothing but the amount of air theoretically required to burn 1 kg of a material completely. Okay. That is important. Stoichiometric air is another important terminology. So, some terminology also you will see in when you go through this. Then you have standard heat of combustion. See, standard heat of combustion specifies the way the particular quantity is measured, the standard heat of combustion is measured. That is, it is the heat released when 1 kg of material which is in a standard condition. What is standard condition? 1 atmospheric pressure and 298 Kelvin. This standard condition is at which the reactants are present first, then products are formed. Then the products are also cooled to 298 Kelvin. Okay. So, understand there is a reactant mixture, methane and air, kept in a container or a reaction chamber with a initial condition of 1 atmospheric pressure and 298 Kelvin. Now, when you cool it, when you form the product, ignite it and products are formed, when you cool the product to 298 Kelvin, so that means heat is released out. So, that means the exothermic reaction, heat is released. The heat is released to the atmosphere. So, when you take out all the heat, then the products are cooled to 298 Kelvin. So, what is the amount of heat which is taken out? That is called standard heat of combustion. Okay. So, the heat released when a particular amount of 1 kg of material is completely burnt, starting from 1 atmospheric pressure and 298 Kelvin, forming products are cooled to 298 Kelvin. What is the heat release? That is the standard heat of combustion. And This is same as calorific value. Okay, and the calorific value can be now classified as lower calorific value and higher calorific value. Okay, so if you see any reaction, combustion of methane, methane reacts with 2 moles of oxygen, and so air is basically 1 mole of oxygen and 3.76 moles of nitrogen. So 2 moles of oxygen is required to completely burn CH4 to CO2 and 2H2O plus whatever nitrogen will remain. Two into 3.76 times, 2 into 3.76 times N2 will remain. So this is the stoichiometric equation that says to burn a given amount of, say here, 1 kilomole of CH4, how much oxygen is required? 2 moles of oxygen is required, but in the air there will be some amount of nitrogen. Okay, so air contains 21% O2 and 79% N2. Okay, so that is written in terms of number of moles as 1 mole of oxygen and 3.76 moles of nitrogen. So in this reaction, when the reactants are at 298 Kelvin, 1 atmospheric pressure, reaction is allowed to complete, products are cooled to 298 Kelvin, what you get is called the standard heat of combustion, which is same as calorific value. Now, there are classifications of calorific value as lower calorific value. You see that in the product there is some water which is formed, H2O. If this water is in basically liquid phase, then what you get is higher calorific value, because water is formed in vapor phase. Now, when you extract heat, you extract the latent heat of this water which is formed also, so that the water goes to condense and goes to liquid state from the vapor state. So you extract more heat to condense the water also. When water condenses, that heat also you try to take out. On the other hand, if the water is in vapor state, then what you get is a lower calorific value. Okay, so I'll stop here.